Okay, let's check out another example involving, again, revenue and profit. Well, cost, revenue, and profit. So these hamburgers were $4 each. They sold an average of 10,000 on game night. When they raised the price to $4.40, the sales dropped off to an average of 8,000 per night. So we can look at that as two data points, right? If it's $4, we sold 10,000. And the second data point, if we raise the price to $4.40, they only sold 8,000, right? Which makes sense. You raise the price, you won't sell as much. Assuming a linear demand curve, find the price of a hamburger that will maximize the nightly hamburger revenue. So we're looking for the price. One other key thing here, so I kind of wrote it, not necessarily intentionally, but they don't specify which is X or which is Y. Right? Like, I don't know, what I'm saying is I don't know if I should actually do it this way. So should my two data points be price and then the number sold, or the number sold, 8,000, with the corresponding price? Okay. I don't know which is X or which is Y, so I'm going to read a little further into this. Where in part B, the variable cost is 60 cents per hamburger. So that tells me, like, I'm kind of seeing it that, right, revenue is X times P, that the X should be the number of sales here. Now, I did them both ways. They both work out. Okay, ultimately, I think, changing one X and Y will save you a step on one question, and then flipping it the other way would save you a step in the other question. So really, it doesn't matter as long as you stay consistent with your units. I'm going to go ahead and make X. Make X the sales. Okay, how many hamburgers were sold? And I'll make Y the price. Okay. So therefore, I'm going to use this one. So assuming a linear demand curve. So if I kind of modeled this, right, X and Y, this is the price, this is my sales. Then as the price goes up, right, the sales drop. So over here, when I sold 10,000, the price was lower. But if I don't sell as much, it's because the price was higher. So I'm getting some sort of curve like that. And that makes sense too, because if I think of a really, really high price, right, I might not sell any. If they were $100 a burger at this city sports arena, you probably are not going to sell any. Okay. However, if you made them free, right, your sales would skyrocket. 50-cent burger night, right, everyone's buying them. Okay. So with that said, let's get our equation, a linear demand curve, y equals mx plus b. Okay, I know m is the y2 minus y1 over x2 minus x1. So 440 minus 4, so that's 40 cents. Over 8,000 minus 10,000, so negative 2,000. And dividing that, I'm going to go ahead and make it a decimal for now. We get negative 0.002. So what does that mean for every, this isn't even a penny, but for every that much drop, partial penny, right, you'll sell one extra burger. All right, B in this case, we don't have, I don't know the y-intercept. I don't know where x is 0. So we can just substitute that in. We could use the other point slope, right? Y minus y1 equals mx minus x1. We'll go ahead and do that formula. Y minus, I like the first set better, y minus 4 equals negative 0.0002, x minus 10,000. Okay, distributing that through and adding the 4, we get a negative 0.0002x. So that'd be a 2 plus 4 is 6. Okay. So now r of x, right, this is my p, right? Y, I call y the price, so this is my p. So r of x equals x times p. R of x equals x times this, negative 0.0002x plus 6. Now, really quick, we've done quite a bit, and I'm jumping around a bit. Why am I doing that? Because reading it again, find the price of a hamburger that will maximize the nightly hamburger revenue. So I'm trying to maximize revenue, right? That's what I want to max. And revenue is x times p. Okay. So we would have negative 0.0002x squared plus 6x. That's my revenue. And we're trying to maximize that, do derivative. Negative 0.0004x plus 6. And that's max or min. Right? We get an extreme at 0. So add the 0.004 to the other side. 0.0004 x equals 6. Divide it. And you get x equals 15,000. Really quick, we need to verify this is a max. Second derivative, again, really easy. Second derivative of this is negative 0.04. We only care that it's negative. So concave down, max. Right, so we are good, it is a max. Looking here as well, is there any restriction? Well, looking at this graph, I know I don't need to check endpoints because the very right endpoint here would mean the price is 0, right? Sure, I'd have a lot of cells and I do have to restrict the domain because I can't go down to negative, right? So there's an endpoint, but I know it's not going to be a max by charging nothing. Then the other endpoint is that somewhere up here, right, our y equals mx plus b, our y-intercept, our initial value. But if I sold nothing, right, 0 cells, doesn't matter if I sold $1 million burger. If I didn't sell any times 0, it's 0. So endpoints, and this is often the case in the examples, they're not going to produce a max. Okay. Now, reread the question though. It says find the price of a hamburger. 15,000, right? That's not the price. That is how many are going to be sold at a given price. So the price actually was our other function, right? Y equals negative 0.0002x plus 6. So plug that 15,000 in. Just do it now. Plug 15,000 in for x plus 6. And we get 3. So using a calculator, we get 3. I didn't do that in my head. So the price is $3 per burger to maximize revenue. Now this example so far had nothing to do with the cost, right? So we just want to know how do we maximize the amount we bring in. So part B is where a little stipulation is added. So the concessionaire has a fixed cost of $1,000 per night, and the variable cost is 60 cents per hamburger. Find the price of a burger that will maximize the nightly hamburger profit. So let's change colors here. We'll go purple. B. Okay, now we're trying to maximize profit. Profit is revenue, take away the cost, right? We know, we've seen that. Revenue minus the cost gives us profit. So the revenue we had above, the negative 0.0002x squared plus 6x, take away this cost. So 1,000 per night and 60 cents for every burger, right? 60 cents times x. This here is the cost, this here is the revenue. Now we need its derivative because we're trying to maximize profit, right? And this derivative for revenue I did above. So rather than combining like terms, let's just take the derivative we had above, negative 0.0004x plus 6. But now we have this cost. Derivative of 1,000 is 0. Derivative of 0.60x is 0.60, but remember it's negative because we have to distribute. So minus 0.6. 6 minus 0.6 is 5.4 or $5.40. We're setting that equal to 0, right? So let's add, just like we did above, the 0.004x. And now when you divide, what do you get? Up, I had it written down, 13,500. Okay, I definitely couldn't do that in my head. So 540 divided by 0.004 is 13,500. Again, we're finding the price, right? Not how much was sold. So we need to sell 13,500. Go back to that price function. A negative 0.0002 times x, so times 13,500 plus 6. And again, using a calculator, that's negative 27 plus 2.7, sorry, plus 6. So we get $3.30. So if there were no costs, we got $3 per burger. We got to raise the price a little bit to $3.30 per burger to maximize profit.